Welcome to today's deep dive. You know, Usually when we walk onto the floor of a modern precision manufacturing plant, the overwhelming feeling is one of just absolute rigid control.
Oh, for sure. It feels completely clinical.
Right. Like we see these massive multi-ton CNC tapping centers, and they're carving out aerospace components or medical implants from like solid titanium. And the assumption is totally binary. You feel the machine perfect code, and you get a geometrically perfect part.
Yeah, we tend to treat these heavy machines as, well, immovable constants. I mean, a cast iron machine block feels like the literal definition of permanence.
But the reality inside those cutting chambers totally destroys that illusion. We're actually looking at an environment that is constantly shape-shifting. It's bending and basically warring against its own
Yeah,
physics.
it's incredibly dynamic in there.
Exactly. So we're pulling from a highly technical engineering excerpt today titled Simply Pasted Text, which breaks down the thermal deformation of CNC tapping centers. And our mission for today's deep dive is to map out this hidden microscopic war going on inside precision manufacturing.
Which is such an important topic.
Right.
I mean, heat is basically the ultimate invisible nemesis of tolerance.
Okay, let's unpack this. Because, thermal deformation sounds like really dry engineering jargon. Why should you, our listener, care about this?
Well, whether you are managing a high-volume factory or looking into tech investments, or honestly, even if you're just marveling at how flawless the metal casing of the device in your pocket is, understanding this invisible thermal battle is key. It completely recontextualizes modern engineering.
Because the heat is actively fighting us, right?
Exactly. We're dealing with an environment where heat is actively trying to rewrite the physical geometry of your equipment, literally every single millisecond it operates.
Wow. Okay, so to defeat the enemy, we have to understand its origin first. And the source text breaks down this trinity of heat sources that drive the thermal deformation. So first up, we have internal kinematic friction.
Right, the moving parts.
Yeah, we're talking about heavy spindle bearings spinning at like upwards of 20,000 RPMs.
Which is incredibly fast.
Yeah.
And the mechanical reality there is that, well, no bearing is completely frictionless.
Right.
At those rotational velocities, the mechanical shear within the bearing lubricant itself generates this massive thermal load, and that heat, it bleeds directly into the spindle shaft.
Okay, so that's the first source.
Yeah, and then you combine that with the violent physical act of cutting the metal itself.
Hmm.
I mean, machining isn't really just cutting. It's the localized plastic deformation of metal.
So you're literally forcing the metal to yield.
Exactly. You are forcibly breaking those metallic bonds, and that kinetic energy instantly converts into intense localized heat.
Which radiates right through the cutting tool and into the machine structure.
Yeah, exactly.
Okay, and the third pillar of this heat trinity is honestly just the ambient environment of the shop floor itself, right? Like a loading bay door opens, the temperature swings just a few degrees, and the cast iron column of machine literally expands.
It does, and the source is very clear here. These three heat sources, if you leave them unmitigated, they will systematically destroy your process capability index,
Mhm.
or your CPK.
Which is a nightmare scenario for any process engineer.
Oh, what absolute nightmare. A degraded key basically means your standard deviation has widened, and you can no longer guarantee that your process will stay within the specified tolerance limits. The source actually describes the solid steel of the machine behaving essentially like hot plastic.
That hot plastic effect is such a phenomenal visual, especially when the source talks about spindle thermal elongation.
Right, the stretching.
Yeah. Like, imagine you're drawing a perfectly precise blueprint with a pen, but the physical plastic of the pen is magically stretching longer in your hand while you draw. The ink is obviously going to land outside the lines.
That's a perfect analogy.
Mm-hmm.
And because of the machine's vertical orientation, that hot steel spindle expands straight down.
Directly along the z-axis.
Exactly. And that thermal slope triggers this catastrophic domino effect on production.
Let's look at a standard blind hole operation, for instance.
Okay, lay it out for us.
So an operator programs a precise 5 millimeter depth. But over the course of a shift, that spindle acts as a heat sink for the bearing friction, and it stretches downward.
Because it's getting hot.
Right. The machine executes the exact same z-axis command in the code, but the tool physically pushes 5.1 millimeters into the material.
Oh, wow. And a 0.1 millimeter drift? I mean, on a 10,000 part aerospace contract, that doesn't just ruin a single component. It completely destroys batch consistency.
It really does. The source outlines this brutal scenario where an operator runs a freshly calibrated, completely cold machine. And the first 10 parts pass the depth gauge perfectly.
Right, because everything is stable.
Exactly. But 4 hours later, the constant friction and cutting shear have basically baked the machine block. So it's running hot now.
Yeah, and the program remains identical. The raw aluminum or steel is identical. Yet the final 10 parts of that shift fail QA because the blind holes are suddenly out of tolerance.
Because the machine physically shape-shifted over those 4 hours, ruining the yield?
Exactly. And the deformation isn't purely vertical either. Those localized heat pockets cause the spindle housing to warp asymmetrically.
Which introduces radial runout.
Right, wobble. The tool tip begins to trace an ellipse rather than a perfect circle.
Oh, man. So it's chewing into the sides of the hole.
Exactly. That radial runout means the tool is aggressively chewing into the sidewalls of the bore, so you immediately fail the pin gauge test because the hole is now oversized.
Right.
And worse, that eccentric rotation induces harmonic chatter. It leaves these aggressive, visible marks on the metal, completely destroying the required surface roughness metrics.
Wow. But wait, if solid steel is bending and stretching enough to ruin a part like that, how do the operators even know it's happening before an entire batch is totally ruined? I mean, catching a 0.1 millimeter drift on the final QA table is way too late.
Oh, it's entirely too late. The material cost is already sunk at that point.
Right, and you can't just, halt a continuous production line every 2 hours to let the cast iron take a nap. So how are they catching this while the spindle is literally buried in a block of titanium?
Well, halting production destroys your margin. So process engineers rely on real-time diagnostic and compensation strategies to basically fight the fire while it's burning.
They have to make the invisible thermal loads visible.
Exactly. They deploy high-resolution infrared thermal imagers to map out the thermal gradients across the machine block during operation.
Oh, that's smart. And the source actually notes that it's entirely common to identify a 15 degrees Celsius differential between the spindle shaft and the main machine bed.
Yeah, and that massive thermal gradient is exactly what causes that asymmetric warping we talked about.
Right.
So to counteract it, engineers perform baseline calibrations using laser interferometers during planned downtime. By measuring the physical displacement of the spindle at varying temperature nodes, they construct a high-fidelity thermal map.
Like a database of how the machine bends?
Exactly. It's a lookup table specifically tied to that machine's unique structural DNA.
Okay. So what does this all mean for the actual production run?
It allows the CNC controller to fight the physics dynamically. The source details the z-axis offset function, and the underlying logic here is just brilliant.
Yeah, this part blew my mind.
Right. The thermal lookup table tells the software that, say, a 10-degree temperature spike in the spindle housing correlates to a physical downward stretch of 0.1 millimeters.
Okay.
So the machine's internal thermistors detect that 10-degree rise. And in a fraction of a second, the CNC algorithm actively lifts the z-axis coordinate by 0.1 millimeters.
Wow. So it is deliberately retracting the entire spindle assembly to mathematically cancel out the metallurgical expansion of the steel.
Exactly. The software is effectively forcing the tooltip to hover in the exact same mathematical coordinate in 3D space. It's actively fighting the material's physical shape-shifting in real time.
That is just incredible. But, the machine is only half the thermal equation, right? Because the kinetic energy from the cut is also bleeding into the raw workpiece.
Oh, absolutely. The specific heat capacity of the raw material dictates how aggressively it will swell during the machining cycle.
Because it's absorbing heat, too.
Yeah, sensitive alloys expand remarkably fast when subjected to that sheer heat. So the source details a procedure where sensitive raw billets are staged in a temperature-controlled environment.
They pre-cool them, right?
Exactly. Pre-cooling the material to a stable 50 degrees Celsius before it ever enters a cutting chamber.
Setting that cold thermal baseline buys the operator time. The material absorbs the cutting heat and rises toward room temperature rather than swelling beyond its dimensional limits while the tool is actually engaged.
It's a really elegant solution. But, firefighting with real-time software offsets and material pre-cooling is undeniably clever. But relying purely on algorithms to counter physical deformation carries inherent risk.
Yeah, I imagine constantly fighting heat with software seems exhausting. And risky. Like, what if a sensor fails?
Exactly. If a thermistor degrades or the lookup table drifts, you are instantly generating scrap. So the permanent solution shifts from firefighting to fire prevention during the capital procurement phase.
Ah, so you engineer the heat out of the system before it even exists.
Precisely. This requires specifying tapping centers that are built with inherent thermal mitigation. And the source goes deep into structural design here, starting with thermal symmetry.
Right. Symmetrical casting is foundational. Like if the column and the spindle box mirror each other perfectly, that inevitable thermal load diffuses evenly across the entire structure.
Yeah, instead of a concentrated hotspot bowing the cast iron to one side, the uniform expansion maintains the geometric integrity of the axis. The tool just stays perpendicular to the table.
Which makes total sense. But here's where it gets really interesting. The structural engineering goes further, utilizing materials specifically chosen for their atomic properties. The source heavily emphasizes Invar alloy.
Oh, integrating Invar components into the critical measurement and structural pathways totally changes the game.
For those who don't know, what is Invar?
It's a nickel-iron alloy,
Yeah.
famous for its uniquely low coefficient of thermal expansion, because of a phenomenon called the Invar effect, where the alloy's magnetic properties internally counteract the thermal vibration of its atomic lattice. It undergoes virtually zero volumetric expansion at standard machining temperatures.
Wow. So you are neutralizing the thermal drift at the molecular level.
Exactly. And alongside Invar, the source details the strategic placement of ceramic insulation plates right between the drive motor and the spindle housing.
Because metals are exceptional thermal conductors, right?
Right, because of their free electrons. Ceramics, however, rely on tightly bound covalent and ionic bonds, which severely restricts heat transfer.
So by placing a ceramic barrier there, engineers are creating a physical thermal quarantine. They block the stator heat of the electric motor from ever reaching the cold, sensitive bearings.
Exactly. But, even with Invar and ceramics, the kinetic energy of the cut and the friction of the bearings still generate thermal loads that require active removal.
Right. You still have to deal with the heat being created in the moment. So the specified tapping centers employ closed-loop oil chillers.
Yeah, these active cooling systems pump highly regulated, temperature-controlled oil through an intricate jacket surrounding the spindle cartridge. By continuously circulating this fluid, they aggressively extract the heat.
Ensuring the spindle core remains in a state of thermal equilibrium regardless of the heavy cutting loads.
Exactly, so the machine hardware is optimized. But the source makes it clear that the operator's machining parameters must also adapt. The physical act of shearing the metal has to be managed.
Right, and they implement a low-speed, high-feed strategy for this, dropping the cutting velocity from, say, 200 meters per minute down to 150 meters per minute.
Because high-speed cutting generates immense friction at the tool chip interface. By reducing the surface footage, you lower the baseline friction.
And simultaneously, increasing the feed rate means a thicker chip is sheared off with each rotation.
Which is key. The physics of metal cutting dictate that the majority of the heat is actually carried away within the evacuated chip rather than bleeding into the workpiece.
Oh, so a thicker chip acts as a better heat sink.
Exactly. And alongside those modified feed rates, they employ MQL. That's minimum quantity lubrication.
Instead of just drowning the cutting zone in hundreds of gallons of traditional flood coolant.
Right. MQL delivers a highly compressed, finely atomized nano-oil mist directly to the cutting edge. The efficiency of MQL lies in its tribology.
How so?
Well, traditional flood coolants often fail to penetrate the vapor barrier created by extreme heat at the cutting edge. But the microdroplets of an MQL mist, delivered under high pneumatic pressure, they easily pierce that boundary layer.
Oh, wow.
Yeah, they provide targeted lubricity directly between the tool rake face and the chip.
And the source claims this highly targeted lubricity reduces the frictional heat of the cut by an incredible 50%.
It's massive.
But wait, what's fascinating here is looking at this low-speed strategy. I have to challenge this. Slowing the spindle from 200 to 150 meters per minute undeniably reduces the part per hour output of the machine, right? And the initial instinct in any manufacturing environment is to maximize throughput. Doesn't slowing down fundamentally hurt the bottom line and lose money?
It's a common assumption, but measuring profitability solely by spindle speed is a trap.
A trap.
Yeah. The true metric is the yield of accepted parts. Running at 200 meters per minute might look great on a spreadsheet, but if the resulting thermal deformation drops your CPK and 50% of that batch fails QA for Z-axis drift or surface chatter, your actual throughput is abysmal.
Ah, I see. You are just accelerating the production of highly expensive scrap metal.
Exactly. By backing the velocity down to 150 meters per minute, utilizing the thicker chip load to evacuate heat, and deploying MQL mist to slash friction, you guarantee a geometrically stable, 100% accurate production run.
So maximizing your yield is vastly more profitable than maximizing your raw cutting speed.
100%. A slightly slower perfect run beats a fast, scrap-heavy run every single time.
Okay, so we've engineered a beautiful theoretical system here. We have thermally symmetrical castings, Invar alloy structural components, covalent ceramic heat shields, active closed-loop oil chillers, and optimized MQL cutting parameters. The heat is managed.
Theoretically, yes, but the source pivots to a really harsh reality here, mechanical degradation.
Right. The physical world inevitably introduces entropy. Over thousands of hours of operation, the baseline thermal signature of that machine will eventually drift.
Yeah, a tapping center that held micron tolerances and ran thermally stable on day one will literally bake itself to death by day 1000 if you leave it alone.
Yeah.
The preventative maintenance protocols are just brutal.
Let's dig into that, starting with spindle balancing. The source mandates checking the dynamic balance of the spindle every 500 operational hours.
Which is crucial. A 20,000 RPM spindle requires absolute rotational symmetry. Even a microscopic imbalance like, maybe from a slight tool crash or just minor bearing wear, introduces high-frequency vibrations.
And those micro vibrations hammer the bearing raceways, dramatically increasing the kinematic friction.
Right. The bearings begin to skid rather than roll smoothly, and that mechanical shear translates directly into massive thermal spikes. So every 500 hours, technicians deploy specialized accelerometer arrays.
To measure the vibrational signature of the rotation.
Exactly. They then add tiny microweights to the spindle collar to counteract the asymmetry, returning the vibration levels back to factory specs. And the source actually notes that a perfectly balanced spindle, free of harmonic vibration, will run virtually cold.
Wow, completely cold. You are eliminating the friction at the molecular level.
Yeah. But, ensuring the mechanical rotation is smooth doesn't matter if the active cooling systems fail.
Right. And the source's description of coolant degradation immediately brings to mind a biological cardiovascular system.
Oh, totally.
The coolant flow is basically the bloodstream of the tapping center, right?
Yeah.
Continuously circulating to pull thermal loads away from the vital organs. And dirty coolant is like cholesterol clogging the arteries.
That is exactly what happens. Tribology plays a huge role here as well. The coolant doesn't remain pure. During operation, tramp oils from the machine's ways, microscopic metallics swarf from the cutting zone, and even bacterial growth begin to alter the fluid's viscosity.
So the coolant basically degrades into a thick, abrasive slurry.
Yeah, it's the mechanical equivalent of arterial plaque. This sludge clings to the inner walls of the machine's intricate cooling jackets.
Which restricts the flow rates and drastically lowers the fluid's ability to absorb heat.
The thermal transfer coefficient just plummets. So to combat this, the maintenance discipline requires a physical purge. Technicians have to flush the entire internal pipe network with high-pressure, clean water monthly to strip away that accumulated sludge.
Wow, every month.
Yeah. Furthermore, they continuously monitor the filtration banks. They specify replacing 5-micron water filters.
5 microns. A piece of swarf 5 microns across is literally invisible to the human eye. But if left in suspension, that microscopic metal dust turns the coolant into a liquid abrasive that simultaneously traps heat and destroys the coolant pumps.
Right. Maintaining that filtration is non-negotiable. If we connect this to the bigger picture, what this source ultimately reveals is that extreme precision is not something you simply purchase. You can't just buy a thermally stable machine and walk away.
It's an ongoing process.
Exactly. Precision is a relentless, ongoing discipline. If you allow the coolant to degrade, or you ignore a slight spindle vibration, the thermal baseline shifts. The heat inevitably returns, the z-axis drifts, and your tight CPK just evaporates.
It is a constant, unyielding campaign against entropy. Man, so to summarize the terrain we've covered today, we began by defining the microscopic war zone of thermal deformation, right? Tracking how kinematic friction, ambient temperatures, and the violent shear of metal cutting turn a solid cast iron structure into an expanding hot plastic geometry.
Yeah, and we analyzed the systemic fallout when a 0.1 millimeter z-axis stretch fundamentally ruins batch consistency and destroys surface roughness.
Right. And then we looked at the tactical countermeasures, like mapping the thermal gradients with laser interferometers to feed dynamic z-axis offsets directly into the CNC controller on the fly.
And physically quarantining the heat through thermal symmetry, those Invar alloys, and ceramic insulators.
We also talked about optimizing the machining parameters, using low-speed, high-feed tool paths, and penetrating the thermal boundary layer with MQL nano-oil mist to evacuate the heat.
Right. And finally, we anchored all of this high-level engineering in the gritty reality of preventative maintenance, like dynamically balancing spindles every 500 hours and aggressively flushing the machine's cardiovascular system to prevent abrasive sludge from insulating the cooling jackets.
The sheer amount of engineering capital dedicated to managing just a few degrees of temperature fluctuation is absolutely
It
staggering.
really is a monumental achievement of modern manufacturing.
So to you, our listener, the next time you hold a perfectly machined metal device, consider the invisible forces at play. That flawless metal surface is the physical manifestation of a victorious thermodynamic war.
It really is. And, that actually leads to a really profound consideration for the future, building on these sources.
Oh, what's that?
Well, everything we have discussed today, the interferometers, the MQL mist, the INVAR lattices, it's all designed to control thermal expansion at the microscopic, millimeter, and micron levels. However, as advanced manufacturing inexorably pushes down into the true nanoscale, literally building structures atom by atom, the paradigm shifts entirely. At that scale, the inherent thermal vibration of the atoms themselves becomes a disruptive force.
Wow. Wait, really?
Yeah, so the question is, will the inescapable thermodynamic noise generated by any mechanical system ultimately form an absolute insurmountable physical limit to human engineering precision?
Oh, wow. An unbreakable microscopic ceiling on our technological progress based entirely on the physics of heat.
Exactly. Something to ponder.
That is a brilliant and truly unsettling concept to leave off on. Thank you for joining us on today's deep dive into the hidden world of thermal deformation. We will be back next time to pull back the curtain on another complex system. Until then, stay curious.